if I draw an air column, it's like a pipe with two open ends. What do we call that in our column? Is that an open air column or is that a closed air column? Yeah, that's an open air column. Now, that doesn't help us to actually solve this problem, but it does help us to interpret the question. The question says you have an open air column. We have to recognize that that's what we're dealing with, not this. This would be a what? It's a closed air column. Even though it's open at one end, we're still going to call it a closed air column. The other scenario that we can see is when we have two ends that are fixed, not an air column per se, but maybe you've got a string that's in between these two ends. Okay, that's going to be pretty clear what you're dealing with then. Okay, it's a string that's attached at both ends. Okay? It behaves the same as an open air column, but just looks a little bit different. Let's draw the first harmonic, the first resonant frequency, the first standing wave that we would see in all three cases. Okay, let's draw it for this one first, because that's the first one that we did a couple of days ago. The first harmonic is going to look like this. You've got a big bump in the middle. What do we call that big bump in the middle, by the way? It starts with an A. We call it an antinode. What do we call these spots at the end that are fixed, that are attached? Good. We call them nodes. So there's two nodes and there's one antinode. The string appears when it's going back and forth, and you guys saw this in the demonstration on Monday. The string appears to be in two places at the same time. It appears to be up at the top and down at the bottom, and that's why I have it drawn the way that I have, but it's not. You guys know that it can't be here and here at the same time. It's one place or the other or somewhere in between. It just looks like it's in two places at the same time. Let's draw the next one here. The next standing wave that we drew was for the closed air column. Remember, we have to have what at a closed end? A node or an antinode? We have to have a node at a closed end. So that means it's going to be like this at the closed end. But we have to have an antinode at the open end. So the first standing wave that we can see for this one is going to look like this. It's about half of what we see in the first standing wave with the guitar string or the whatever string. Right? We've got one node, we've got one antinode. And of course it's only a quarter of a wave instead of a half. Finally, the third one is when we have a pipe where we have two open ends. It's like literally taking a pipe, going across the end of it. The first standing wave that we're going to see is it like this? Is that right? What's wrong with that? Okay. If both ends are open, what do we have to have at both ends? Got to have antinodes at both ends. So let's not draw it like this. Let's draw it like this. Instead of having one antinode, we're going to have two antinodes. It's going to look something like this. Now, for each of these, let's determine what the length of it is in terms of the wavelength. Let's say L is literally the length of the column. In this case, we would say L is equal to how many waves? It's a half a wave, right? It's a half of a wave. Okay, it goes from node back to node. If it was going to be a whole wave, it would go like this. So we've got a half of a wave there. What do we have in the second scenario here where we have the closed air column? L is equal to, how much of a wave is that then? Good, it's a quarter of a wave. Okay, we're going halfway on what we did on the guitar string, so it's going to be a quarter of a wave. And what's this one going to be up here? L is equal to, going from crest to trough, basically, so that's going to be 1, not a whole wave, right? If we're going from crest to trough versus from crest all the way back up to crest, okay, that would be one complete wave, okay, from start to finish, where it repeats itself. This is going to be a half wave. Good. Now, we want to rearrange each of these to solve for lambda. Lambda here would be 2 times L. This would be 4 times L. And this would be 2 times L. And then we take our wave equation that we learned way back before Christmas, seems like forever ago now, almost a month ago, before Christmas, and then we sub in lambda, or 2L, or 4L, or whatever it is, for lambda. So it's going to be F is equal to V over lambda, or V over 2 times L. This one would be F is equal to V over lambda, or V over 4L. And this one would be V over lambda, or V over 2L. Now, the next harmonic, these are all the first harmonics, right? The next harmonic that we're going to see with the guitar string, where the guitar string is fixed at both ends, is going to be what? What are we going to call it? This is the first harmonic, the first harmonic, and the first harmonic. This next one is going to be called the second harmonic. And the value of F2 will always be equal to twice the value of F1. So if we have the value of F1 from this equation, we can double it and get the value of F2. Same thing over here. The next sound that we hear, or the next standing wave that's set up, will be the second harmonic, and it's going to be twice the value of the first harmonic. What's the next one going to be when we have a closed air column? What's the next one going to be with a closed air column? The third harmonic. So we're going to call that F3. Where's the second harmonic? Yeah, there is no second. When we have an open air column, or when we have a guitar string that's attached at both ends, or some other string that's attached at both ends. Basically, when both ends are the same, then we have a first, second, third, 34th, any harmonic you want. But when you have a closed air column where one end is open and one end is closed, and the ends are different, you only have the odd number of harmonics. You don't have the even. Does that make sense? Ring a bell? Now there is one more equation that we saw yesterday that helped us to sometimes analyze these problems with air columns. So we sometimes saw this other equation, 331 plus 0.6 times t. What was that for? At standard pressure, this gives us the speed of sound. The speed of sound varies with the temperature. And at standard pressure, it's 331 plus 0.6 times t. Now, why doesn't that equation work with this? Why don't we use it with this one right here? Why don't we use it only with the air columns? Yeah, this is a guitar string, or this is, remember we talked yesterday about the doorbell? If this is the doorbell, the piece of steel, and it's like the doorbell that makes the ding or the dong, okay, then the speed of sound is dramatically different. Is the speed of sound going to be smaller or bigger in steel or in a guitar string, whatever it's made out of, than it would be in air? Bigger or smaller? The speed of sound is going to be bigger in steel or in something solid than it would be in air. So I don't know what the speed of sound would be. Somewhere in the range maybe of about 1,500 meters per second as opposed to 330, 340 meters per second. But it certainly can't be found by this equation, 331. Good. This one's on your data sheet. Okay, you're allowed to use it, but just make sure that you know when to use it. It's the speed of sound in air. If you need this speed, you can't use it that way. Okay, there was some questions that you worked on yesterday from your worksheet. The first worksheet that we'd worked on a couple of days ago but wasn't assigned as homework, but then the second worksheet that we did yesterday. Any issues with any of those questions on either of those worksheets? Yep. Number 8 on the first one. Just taking out my worksheet here right now, Lane. Was that one of the ones that we assigned? I'll tell you in a second when I dig out mine. Yes, it was Monday. Okay, so we're taking a look at question number 8 on the first worksheet. It's page 227 at the bottom of the page. It says the fundamental frequency of a string that's 25 centimeters long is 441 hertz. The fundamental frequency, what's another word for the fundamental frequency? What's another word for the fundamental frequency? The first one is the first harmonic. Good. It's 25 centimeters long, and the fundamental frequency we're going to call F1 is 441 hertz. Let's make L right away 25 centimeters. Although we know we're going to convert that to meters, so we might as well do that now. In order to produce the same, in order to produce a fundamental frequency using the same string of 525 hertz, what length do we need? How can we have two different first harmonics? In all the diagrams we drew, we had an equation for the first harmonic, and it didn't look like we could have two of them. We could only have one of them, right? You pluck a guitar string. You hear, let's say, the first harmonic. How do you change the value of that harmonic you hear? Put your finger on a fret. Okay, that's going to change the value of the first harmonic. The speed of the wave in that guitar string hasn't changed, but the frequency of the wave that you hear has changed because the resonant frequency of the string has changed, because the length of the string has changed. So we do have two different first harmonics here, but not at the same time. The first harmonic initially is 441. We change the length of it, it will change the resonant frequency and therefore make the first harmonic a different value. So what are we going to do here to find L? Well, let's draw it out. Let's draw it out first. There's the first harmonic. Okay, we know that L is equal to 1/2 lambda, and lambda is equal to 2 times L. F is equal to V over lambda, or V over 2 times L. There's my equation. We know the speed of the wave in both cases is going to be the same. Like I said just a minute ago, when you pluck that guitar string, it doesn't matter whether you have a finger on a fret or not, the speed of the wave is going to be the same. So let's solve for speed here. In the first case, V is equal to F times 2 times L. It's 441 times 2 times 0.25. That's going to give me 220.5 meters per second. That's pretty slow, actually. I think realistically it probably should be a higher number, but that's what we get here. So the speed of the wave in the first case is 220.5. Well, the speed of the wave in the second case will also be 220.5. Now what we've got to do in the second case is use the same equation, F is equal to V over 2L, to solve for L. The F goes down, the L goes up, becomes V over 2F. So now we've got 220.5 meters per second divided by 2 times 525. Let's see what we get when we do that. 220.5 divided by gives me 0.21 meters, or 21 centimeters. We got that one. Okay. That's the answer that was on the worksheet for it. Good. Good. Let's just take a look at this and see if it's reasonable for a second. I mean, we know that it's the answer, right? Because that's what the answer was on the bottom of the worksheet. But let's say it's a test. We're answering this question on Tuesday's test. Okay, we want to know whether we have the right answer or not. We can take a look at it and see if it's reasonable by looking at the length and how it compares to the initial length. The frequency has gone up. If the frequency goes up, the length of the string must have gone down. Right? Logically, we know that based on our own experience. Okay, we know the last time you plucked a guitar string, whether it was yesterday or 2 years ago, the last time you plucked one, you know when you put your finger on a fret, the pitch goes up. Shorter length, higher pitch. Okay? Talked about that a little bit yesterday, right? Kind of just use your head to see if it's reasonable. You get an answer, see if it's reasonable. Okay? Wayne, is that okay? Any others? On either of those worksheets? No? All right then. We just saw the Big Bang Theory video on the Doppler effect. Sheldon defined the Doppler effect as the apparent change in frequency of a wave due to the relative motion of the source and the observer. I wrote down the exact definition that Sheldon gave us because it was perfect. Okay, when we heard that definition the first time as I played that video, it didn't make any sense to most of you. Okay, people laugh because it's Big Bang Theory, but it didn't really make any sense to most of you until you saw the video of the fire truck going by you. When you saw the fire truck going by you, more importantly, when you heard the fire truck going by you, you saw that the frequency of the wave, the frequency of the siren appeared to change. Didn't change. Once a sound has been made, the frequency always stays the same. But it appeared to change as it was going by you. When a source of a wave is going towards you, it's the frequency that you hear is actually higher than it really is, than the actual sound is. Okay, the guy on the fire truck, the firefighter, hears a certain pitch. As it's going towards you, you hear a higher pitch than that. But as it goes by you, you hear a lower pitch than that. So the guy who maintains the same position relative to the fire truck hears the actual sound. The guy who has the fire truck going towards him hears a sound that is of a higher pitch. The guy who has the fire truck going away from him hears a sound that is of a lower pitch. Right? the apparent change in frequency of a wave due to the relative motion of the source and the observer. Notice I said there of a wave. I think Sheldon actually said the apparent change in frequency of sound. Why have I said of a wave as opposed to just of sound? Yeah. It happens with any wave, not just sound waves. It happens with any waves. The place that it's most observable is sound waves because that's our frame of reference, right? We hear sound waves all the time, and we hear things going by us all the time, and the apparent change in frequency as a result of that. But it happens with the light waves as well. Okay, it's just that the objects have to be moving a lot faster to notice a difference when we're talking about light waves or any other wave. Okay, the Doppler effect happens with any waves. It's just most noticeable with sound waves. Here's the last equation you're going to do this year. Doesn't look pretty though, does it? FD is equal to VW over VW plus or minus VS times FS. It looks kind of ugly. And in fact, it is a little bit ugly, to be honest. What do you think F stands for? Forget about the subscripts for a second, the D and the S. What do you think F stands for? F is going to stand for a frequency, right? V is going to stand for a what? Yeah, speed. Not a velocity so much, but a speed. Sure. So F is frequency, V is speed. FD is going to stand for what frequency? Which frequency is it going to be? Well, there's two frequencies here, right? There's the actual frequency, the frequency that the fire truck made, and then there's the frequency that we hear, that we perceive, or the apparent frequency. FD is going to stand for what? Sorry? F Doppler, yes. Okay. So F Doppler would be not the actual frequency, but rather the perceived frequency or the apparent frequency. Good. So I'm going to write that down. It's the apparent frequency. Okay, we say apparent because the frequency is really still the same. Whatever it was when it was produced is still what it is. We just don't hear it as what it is. We hear it as something different because of the relative motion. The units for that, by the way, would be what? Hertz. Fs is going to stand for the actual frequency or the frequency of the source. I'm going to put in brackets here the actual frequency. I'm sorry? You'd have to be given that value. Nowadays, download an app for your iPhone and and it'll tell you exactly. Listen. I wasn't loud enough to really hear that. That's perfect timing, though, isn't it? Somebody got hurt at a very opportune time for us, so that ambulance would go by the school there. Yeah, I saw it. The frequency of the source, the actual frequency. You could download an app for your iPhone and use the microphone on the iPhone, and it'll tell you exactly what the frequency is. It'll tell you what the frequency that you perceive is, right? So in order to get the actual frequency, you'd have to use that app when the object is stationary relative to you, right? Well, no, as it's moving, it maintains a constant frequency, a constant apparent frequency as it's moving towards you, as long as the speed stays the same, that is. Okay? But then as it goes by you, it changes frequency. So it's not decreasing frequency as it's coming towards you or increasing. It's staying the same. Same frequency as it comes towards you. But then as it goes by you, it changes to a lower frequency, and then it maintains the lower frequency as it's past you. Okay, so if you had your iPhone out and you were measuring the frequency of that, okay, with a whatever app that measured frequency, then yeah, you would notice the change. But you wouldn't notice the change as it was coming towards you. You would notice the change as it was going by you. Does that make sense? So the frequency of the source is Fs, or the actual frequency. The Doppler frequency is the apparent frequency. That's what we hear. Okay, that's what we perceive. Now we get V, W, and Vs. V stands for speed, obviously. VW particularly is going to stand for the speed of what? Vs will stand for the speed of something else. This is a little bit confusing just because of the subscripts that they use. Yep. No, no, it wouldn't actually. VW actually stands for the speed of the wave. So normally it's the speed of sound. Now what's confusing about this is we look at Vs and we think automatically that's the speed of sound, but it's not. Vs is the speed of the source, the speed of the fire truck in the video that you guys watched. And of course the units for that are going to be meters per second. The speed of the wave, it's also going to be meters per second. If you're talking about sound in air, it's going to be somewhere in the range of 330, 340, 350 meters per second. Now, what is the deal with this whole plus or minus thing? If you've got the variables straight, and that's a big if, because it is a little bit confusing to keep straight VW and VS. FS and FD aren't so bad, but VW and VS are kind of tricky. If you've got those straight, then the challenge is knowing when to use a plus and when to use a minus. We never use both. The equation is either VW plus VS or it's VW minus VS. It just depends upon what the situation is. If those two numbers are on the bottom are added together, then we're going to get a bigger number on the bottom. If they're subtracted, then we're going to get a smaller number. Does that make sense? If we get a bigger number on the bottom, then that's going to make FD smaller. If we get a smaller number on the bottom, then that's going to make FD bigger. So if we add these two things together and we get a smaller FD, then that must mean that the source and the observer are moving away from each other. In other words, this is the equation we use whether it's moving toward or away from us, but we make that bottom plus minus thing a plus if the source is moving away from us. In other words, the fire truck has gone by us and is moving away. We make it a negative on the bottom if the fire truck is coming towards us. Because if we subtract those two numbers on the bottom, it's going to give me a smaller number on the bottom, which is going to give me a bigger value of FD, the apparent frequency. Yep. Would that mean that the wave carries the velocity of the source? Yes, but the wave, I wouldn't say the wave carries the source, but yes, when they're moving away from each other, you add them together, the speed of the wave plus the speed of the source, yes. Okay, it's good? Okay. Yeah, it's not the wave per se that's carrying the speed of the source. Let me draw you a little picture here, okay? You guys, this is a little bit more detailed than you got to know, but I'm not even sure exactly what your question is, but this might answer it, okay? We'll see. And if it doesn't, then just let me know, okay? Okay, what do you got when an object is at rest and it's producing a sound? The fire truck is sitting at a stoplight because it can't get through. There's too much traffic. Its siren is going, but it's not moving. Well, here's my fire truck. It's going to produce sound waves that emanate out from the fire truck like this. Okay, if you're standing right over here, you're going to hear the crests of these waves, or not really the crests of the waves because they're sound waves. It would be more like compressions and rarefactions, right? Okay, you're going to hear compression, 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 compression. You're going to hear the actual frequency of that sound that was produced, right? Because the fire truck is at rest and you're at rest. But what happens if you are moving towards the fire truck? You're not going to hear compression, 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 compression. You're going to hear compression, 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 compression. The speed of the wave is still the same, right? The wave is still coming out from the source, but you're walking towards it, so you're going to hear those compressions quicker, in quicker succession, right? You're going to perceive the compressions to be closer together. And if the compressions are closer together, you hear a higher pitch. Does that make sense? It's not really a higher frequency. The frequency of the wave is still the same, but you perceive higher pitch because you're hearing them in quicker succession. Now, the same kind of argument would apply if you were at rest and the source was coming towards you. Okay, the diagram is just a little bit trickier in that case. Okay, if you're at rest and the source is coming towards you, here's position number 1 of the source. It produces a wave. We'll call it wave number 1. Okay, wave number 1 keeps getting bigger. Okay, this is not wave number 2. This is wave number 1, 1 second later. But where's the position of the fire truck a second later? Over here, right? It produces another wave, wave number 2. Now, the frequency of the wave that was made is still going to be the same. But as I'm standing there and this fire truck is coming towards me, what do I perceive? I perceive this and this. I perceive compression, compression in quick succession. If I'm standing on the other side, what do I perceive? Compression, compression in much slower succession because they're further apart there. Does that make sense? And Fraser, I'm not sure if that answers your question or not, does it? Yeah. Well, that's a good question. How fast would you have to be moving to have a change? 0.1 meters per second, right? To make it a noticeable change, it would depend upon how sensitive your ear was to perceiving a change in frequency. And everybody would be a little bit different on that. Okay, if you're moving at, if you're running at 5 meters per second, would you notice a change? Maybe. Okay, it's possible that you'd notice a change at 5 meters per second, and that's a pretty slow speed. Okay, that's a relatively slow speed. So, yeah, you could, but not necessarily. Again, it depends on the sensitivity of your ear. Question? The sonic boom? Yeah, okay, well, you know what, we'll talk about that in a little while. No. Okay, let's briefly go to that since you're pushing me on it. You're making me. Here's the Doppler effect, right? Okay, here's wave number 1, wave number 2. The source is moving. The fire truck is moving to the right, right? It's moving toward the observer there, okay? Well, the fire truck is moving slower than the wave, right? The fire truck is not traveling faster than the speed of sound. If the fire truck was traveling faster than the speed of sound, then wave number 1 would still be where it is, but wave number 2 wouldn't be where it is. Wave number 2, wave number 2 would be over here, because the fire truck is outrunning wave number 1. Does that make sense? Does that make sense? Okay, and you could continue that so that you'd end up with, you'd end up getting like this, right? The pattern would end up going like this. What you end up getting right here is a big area of constructive interference, okay, where the compression of one wave interferes with the compression of another wave, producing a big wave. Okay, you get the same thing right here. So you get, not exactly right there, but more like this. You get this cone that trails this supersonic fire truck or this supersonic airplane, right? You get this cone that follows it. Now, the guy standing on the, let's say this is an airplane, because obviously if you're talking about something supersonic, it's going to be an airplane. There's a guy standing on the ground down here. The guy standing on the ground down here doesn't hear a supersonic, doesn't hear a sonic boom. Okay, the perception is, the common misperception is, when a plane goes past the sound barrier, then that's when you hear the sonic boom. That's not true. You don't hear a sonic boom when it goes past the sound barrier. You hear the sonic boom when the wave, that cone that trails the supersonic airplane, goes past you. So what does the guy right here hear right now? Nothing, because the waves are back here. What does the guy right here hear? Nothing. What is the, kind of run out of space there. What is the really tall guy right here hear?
Nothing.
Oh, okay. boom, right? That's when he hears the sonic boom, because this cone of constructive interference that trails it has just gone past him. So the plane is way past by this point, right? It's way past. Remember, it's going more than the speed of sound. So the plane is, miles away probably until you hear that boom. Okay. You guys, I would bet that none of you guys have ever heard a sonic boom. However, I would bet that all of you guys have all actually seen the exact same effect. Okay? Where have you seen this? Well, let's assume that it's not air in an airplane that's flying faster than the speed of the wave, faster than the speed of sound. Let's assume it's a boat in a lake towing a water skier or something, or just a boat in a lake just out for a ride. The boat's going fast. You ever look behind the boat? What do you see? You see kind of a triangular cone wake of the boat, right? Why do you see that? Because the boat is traveling faster than the water wave, right? The source is traveling faster than the wave. So what is it behind the boat that you see? It's the exact same thing that makes a sonic boom, except it's a water wave. When you're water skiing, this is the hard part, right? This is the hard part. This is easy. Okay, it's easy water skiing in here because there's not very much waves in there. This is the hard part because that's where you get the constructive interference of all the crests of all these waves that were produced by the boat. That only happens because the boat is traveling faster than the wave. If you're going slow in the boat, well, let's assume that you could actually water ski when you're going slow, but if you're going slow enough that you weren't exceeding the speed of the wave, then you wouldn't have that wake. Just like an airplane doesn't have that cone behind it if it's not moving faster than the speed of sound. Yeah, go ahead. Well, if you were right here, it wouldn't be so much of a big deal. If you were right here, it wouldn't be so much of a big deal. I wouldn't want to be an airplane right here. Okay, I'm not sure, to be honest, what would happen to it. You would have a whole lot of turbulence when that sonic boom passed you. Okay. Now, again, that would assume that that wave could catch up to you, that wave was traveling faster than you are. But yeah, I think might cause damage to the plane. I'm not sure. Depend upon the airplane, probably. Like right here, the airplane's right here. No, no, no. It wouldn't be quiet. I mean, there's still sound waves here, right? But it's not this intense boom because this cone doesn't go past you. If you're standing right here, right, this cone is going to go past you like this. If you're standing right here, well, the sound waves are going to go past you, but this cone of constructive interference isn't going to go past you. So you wouldn't hear a sonic boom right there. Okay. And an airplane wouldn't experience that either. Okay, there would probably be some, I would expect to be some fairly unpredictable turbulence back in that area, air doing crazy things, which might mean that you wouldn't want to fly there. I'm not really sure, but it wouldn't be, this intense boom and this giant intense wave. It would be more the changing the waves that would be more of a problem, I think, than the intense wave. Okay. Is it? Where? Yeah. Yeah. Okay. You normally don't hear a sonic boom like that because normally planes that can fly at supersonic speeds don't fly at supersonic speeds over land. They normally fly at supersonic speeds over the ocean, right? But I mean, it's sometimes they do, right? They're not supposed to, but sometimes they do, and sometimes you can hear them. But got a much better chance if record. Yeah, you live at an Air Force base. Yeah. Sorry. I'm sorry. Okay. All right, so that's a bit of a digression, a bit of an extension, I guess, of what we're talking about, the Doppler effect. But Travis, it's a good question because in the end, it is related to the Doppler effect. It's just that it's kind of like the Doppler effect at supersonic speeds. Okay? We're not going to calculate anything with that, but that's exactly what would happen. All right. Guys, the variables in this equation make sense. Which one is S? Which one is W? The speed of the wave, the speed of the source, not the speed of sound. The frequency, the Doppler frequency, the apparent frequency, the frequency of the source, the actual frequency. The big one, though, is the plus and the minus. Yeah, you ever forget that? And I do all the time. Hey, ask me tomorrow when it's plus and when it's minus. If you don't give me 10 or 15 seconds to give it some thought, I probably won't be able to answer that question, even though I've taught this however many times. Okay, I won't be able to do it without thinking about it for 10 or 15 seconds because I'm terrible at remembering things like that. I always have to have a way of figuring it out. Okay? I know that, look, if it's plus, then that's going to give me a bigger number on the bottom, and that's going to give me a smaller number up here. Therefore, I add them together when they're moving away. If it's minus, it's going to give me a smaller number on the bottom. It's going to give me a bigger number on the top. That must mean that they're moving towards each other. That's how I figure it out every time. Okay? Don't memorize it. Figure it out. Yeah?
You also memorize it.
Yep.
Because you're constantly adding the distance between the source.
Yep.
And you're constantly subtracting the distance.
Yep. Yep. The other way you can do it, guys, is, and this sounds kind of odd, but if you forget whether it's plus or minus and you have trouble figuring it out, you can guess. It's okay to guess. Guessing is okay. But you should always do what when you guess? Guess and check. Okay, if you get a number for FD that's smaller than FS, but yet the object, the source is coming towards you, well, you know that's wrong. So it means you guessed wrong. It means you've done a whole calculation incorrectly. You got to go back and do it again, but at least you know that you did it wrong if you take some time to think about that. Okay, let's see what we can do with this. A train is traveling at a speed of 30 meters per second. Fraser, you asked the question, how fast do you have to be running to perceive the difference? You're not going to run at 30 meters per second. I mean, that's pretty fast. But it's still the same order of magnitude that you could be running at, right? You could be running at easily 5 meters per second, easily. You know, even faster than that. You know, Usain Bolt, when he's running at its peak speed, is running somewhere in the range of 15 meters per second, half the speed of that train. Okay. Could you perceive that difference? Yeah, probably. Probably at that speed. The train is traveling at 30 meters per second. Its whistle generates a sound with a frequency of 224 hertz. Can you tell me what that is? Clearly it's a V, but is it Vs or is it VW? Is it the speed of the source or the speed of the wave? Yep. It's the speed of the source. Good. The train, which is the source of the whistle, is moving at 30 meters per second. Now it generates a sound with a frequency of 224 hertz. That's going to be an F, obviously. Fs or Fd, the frequency of the source or the apparent frequency, the frequency that we hear. Yep. Yeah, it's the frequency of the source, the actual frequency. So we're going to call that Fs. You're standing beside the train beside the tracks as the train passes you with its whistle blowing. What change in frequency do you detect? Oh, here's a good question. We're not asking for the final frequency or the apparent frequency. We're asking for the change in frequency, for the pitch of the whistle as the train passes. If the speed of sound in air, the speed of the wave, is 330 meters per second. We're looking for not the apparent frequency as it's coming towards you, not the apparent frequency as it's going away from you, but the change in frequency that you hear. Okay, it's the change in that frequency. Okay, how do we find that? Well, let's get the Doppler frequency in two cases. As it's coming towards us, let's get it. What's the equation? Was it VW or VS? Forget that one. VW over VW, VS. Is it VW plus VS or VW minus VS? Yeah, but we want to know which one is which. We want to keep it straight. Plus or minus? VW minus VS, and we multiply that by FS. Okay, let's get the number there now. Okay, VW is 330. Let's calculate that number on our calculators here now, please. We get a number here that's 246.4 hertz. Now, it's coming towards us. Would we expect to get a lower frequency or a higher frequency as this train is coming towards us? It should be higher, right? Is it higher? Well, the actual frequency is 224. We're perceiving 246. Yeah, it's higher. Fraser, would you perceive that? Yes, 20 hertz is definitely perceivable. Yes. Now let's get the apparent frequency as it's going away from us. That's going to be VW plus VS. The numbers are almost the same, but everything changes by that plus sign on the bottom. Let's calculate what this frequency is now. We get 205.333 hertz. Is that reasonable? Sure, it's going away from us. The frequency goes down. It was 224 hertz. That's the real frequency. When it's coming towards us, we hear 246. When it's going away from us, we hear 205. This seems reasonable. Now we want to find the change in frequency, what we hear or what we perceive as the change in frequency. We're going to subtract the 2. We get 41.1. Is that perceivable? Yes. Okay, you saw the video of the fire truck going by. The fire truck wasn't moving at 30 meters per second, yet you still clearly perceived the change in the apparent frequency as it went by you. This makes sense? Now, one final little thing here. This equation can be kind of ugly to rearrange. You will have to be able to solve for FD. I'll also make you solve for FS. That's not so bad. If you want to solve for FS, let's just take that entire term, VW over VW minus VS, over to the other side by dividing. So this entire term goes over to this side by dividing if you're solving for FS. If I was mean to you, I may ask you to solve for VW. That would be a nightmare for you. Okay, that would be a nightmare for you. Some of you have trouble rearranging V equals D over T. Solving for VW here would be an absolute nightmare. VS wouldn't be much better. I won't make you do that. Okay, you'll either solve for AFD or FS, which is just a little bit harder than that. Travis, question? No? Okay. Got some questions. Once you finish those two questions, we're going to take a look at some check and reflect questions on page. I'll tell you in 2 seconds what page that is. Don't know why it's not written down there. Page 434. Check and reflect questions on page 434. And I want you to do number 1 to 7.